Okay, half-life is the amount of time required for one half of a radioisotope to decay to its daughter product. So you should be familiar with the definition for half-life. And we've got quite a few notes here. Says every radioisotope has a characteristic rate of decay measured by its half-life. So that's important. It's a characteristic rate. In other words, it's based on what the isotope is. Everything's going to be unique or different. And half-life is the amount of time it takes for half of that original radioactive atom to decay into the atoms of a new element. That's what we just said for the definition. And the other half would remain unchanged. So the other half would remain as a parent nuclide, whereas the decayed part would be the daughter nuclide. And here's just a way that you could illustrate what's going on. If you have N is your number of half-lives that have gone by. So let's say you have this magma that cools. Fresh magma, 0 amount of time has gone by. 100% of it is parent isotope. So all of this, these are going to be little pie charts, all of this is going to be parent isotope. And in other words, it's a whole number of 1. You don't have a fraction of it that's going to turn into a daughter isotope. After one half-life, half of it now has decomposed to be this daughter isotope, or decayed to be that daughter isotope. So 50% of it remains as parent, and in other words, that's going to be half. Whereas 2 half-lives go by, now we have half of that parent is now decaying to become the daughter product, and you only have 25% of your parent that remains, which is 1/4. So after 3 half-lives, 4 half-lives, 5 half-lives, we end up getting half of that parent product, parent isotope. So it's going to be 12.5%, which is 1/8, or 6.25%, etc., which is 1/16. 3.125%, which is 1/32, etc. So you just keep decreasing the little pie here that remains as parent, and the rest of this has decayed. And it's hard to draw these little wedges. So there we go. Just pretend that looks good. Okay, so this is our parent in here. So that's one way for us to illustrate what's going on, just for you to be able to see in a pie graph what's going on. And here we have another graph showing the amount of parent that remains compared to the time that's passed by. Okay, so when we go through and we solve half-life problems, I don't think that I put these in your notes, but you can write this stuff down. This is one way to do it, or you can just go back and you can think about this process and figure it out from there, or you can use formulas. So these formulas would not be given to you. You have to be able to come up with this information yourself, as well as these variables, but the variable n stands for the number of half-lives that have elapsed during that time, and T 1/2 is the actual half-life, whereas T is the amount of time that passes by. And then we can talk about the amount of substance. Usually it's its mass, but it's the amount of the substance that originally is there or that remains after a given amount of time. So these are some formulas that we could use. And, oops, the stability of a radioisotope is indicated by its half-life. Just like you would think, the longer the half-life, the more stable it is. If something changes pretty quickly, if it decays really quickly, then that means it's unstable. Half-lives vary from fractions of a second to millions of years. Most artificially produced isotopes have very short half-lives, fractions of seconds. And in the process of this decaying, we know that mass is converted to energy during nuclear reactions, and we've already gone through those calculations. And that was, we used E equals mc² for that. And we can talk about carbon dating. And carbon-14 just happens to be a radioactive nuclide. It's constantly produced in the atmosphere. It has a half-life of about 5,700 years, 5,730. And in the process, it undergoes beta decay. So you have carbon-14 that emits a beta particle and transmutates into nitrogen-14. Let's just keep going here. You can read through this about the process of how how it's used for carbon dating. Now what I'd like to do is spend some time with these examples, and this first little comment here actually probably won't make much sense to you at this point. It says all radioactive decay follows first order kinetics. Well, you have no idea what first order kinetics is because we haven't talked about that yet. I'm going to write it down because you're going to look back at these notes maybe, or maybe you'll refer back to your notes at some point before studying, and this will be something that we learn a couple days before the test anyway. It'll be near the end of the unit. And essentially we learn that first order kinetics says that the natural log of your amount after a given amount of time divided by the original amount equals negative kT. And what we end up seeing is that that half-life is equal to a constant of 0.693 divided by k. Again, you're allowed to look at this and go, I don't get that, that makes no sense. That's okay because we'll deal with this in a few days. Okay, our first example, we're just going to use the formulas that we were given earlier. And let's think about what those were. We said that the number of half-lives is going to be equal to the amount of time that passes by divided by the half-life. And then also the amount that remains after a given amount of time, and if you want, you can put a t there, is equal to your original amount divided by 2 raised to the nth power. So that's where that half comes in. And when we go through here, the question is, how many hours would be required, so it sounds like we're looking for time, would be required for potassium-42 to undergo 3 half-lives, and the half-life of potassium-42 is 12.4 hours. So we're looking for time, and we know that we want it to undergo 3 half-lives, and we know what the half-life is. So it looks like we just have to use this one formula. And we can say that T equals N times our half-life. So that's just going to be equal to 3 times our half-life of 12.4 hours, which equals 37.2 hours. So that one was pretty easy. You probably could have thought through that without using formulas. That's another way to do it, but somehow you'd have to show work at least. Okay, example number 2. The half-life of zinc-71 is 2.4 minutes. If we have a 10-gram sample, how much would remain after 7.2 minutes? So in this case, we're looking for how much remains after a given amount of time. So I'm going to rewrite my formulas again. I know I've got this one. I'm not sure if I'll have to use that or not. We'll have to think about it. And then we've also got our original amount divided by 2 raised to the nth gives us our amount after a given amount of time. So the half-life is given to us as 2.4 minutes. We know our original mass. We want to know how much remains after a certain amount of time. So one of the first, what we're going to have to do here is if we have 7.2 minutes passes by and we know that the half-life is 2.4, looks like we can use that first formula and we can say that the number of half-lives is just going to be 7.2 divided by 2.4, which is going to be equal to 3. So we know 3 half-lives have passed by. So now we can take that and we can plug that in, and we're just trying to solve for our amount after a given amount of time. So that amount is going to be equal to our original amount, which is given as 10 grams, divided by 2 raised to the 3rd power, which is just 10 divided by 8, which equals 1.25 grams. And that's it on that one. A couple more. Actually, let me go back to this. I'm not going to do it now, but this one is a great example for us to be able to use our first order kinetics reactions that we're going to talk about near the end of the unit, so we could always come back and use those formulas with this one and get exactly the same answer. Okay, example number 3. What is the half-life of an unknown radioactive sample if a 66-gram sample decreases to 8.25 grams in 48 minutes? So I know both of my masses, my amounts. I know the time that passes by. I want to figure out the half-life. So in this case, I'm going to say, let me rewrite my formulas. I think that'll make it easier for us to look at. In this case, I'm going to solve for 2 to the n. So I'm going to say 2 to the n equals my original amount divided by my amount after a given amount of time. So 2 to the n equals, my original amount is going to be 66 divided by 8.25, which equals 8. So in this case, you can plug this in your calculator, or you can just figure that out on your own, and you see that n is going to equal, that would be 3. So n equals 3. And so now we can just go ahead and plug that into our first formula. We know n, and then we're looking for half-life, and we know the amount of time is 48 minutes. So we can say that the half-life, that's what we're looking for, is equal to t divided by n. So that's going to be the amount of time that passes by is 48 minutes divided by 3 half-lives. So that's going to be equal to 16 minutes. Okay, we have one more. And in this case, we see that a patient is administered 20 milligrams of iodine-131. How much of this isotope will remain in the body after 40 days if the half-life of iodine-131 is 8 days? So our formulas, and we are looking for how much will remain. So we are looking for A, but we don't know what our half-life is yet. We have to go ahead and calculate that first. So we say that n equals our 40 days divided by our half-life of 8 days, so that's going to be 5 half-lives have passed by. So now if we know 5 half-lives have passed by, we can go ahead and plug it into our second formula, and we can say that A equals the original amount, which is 20 milligrams, and divide that by 2 raised to the 5th power. So that's the same thing as saying 20 divided by 32, and that's going to be equal to 0.625 milligrams. That is it.